In the previous two modules, we had been looking at the state space models. Now, as you know, the state space models are primarily latent variable models, where the observation actually depends on a set of latent variables. And then the latent variables themselves have a time series model, like maybe a AR1 or a ARMA PQ, etc. We have seen different types of standard time series models which can be put in the state space form. And in the last lecture, we had been looking at the estimation problems related to the state space model. These are primarily the Kalman filters, and we have seen that we have a set of equations which we keep updating as we go along to estimate the parameters of this model. What we will do in today's module is that we will be looking at some of the properties and results related to the state space model. Primarily, we will be looking at conditions under which a state space model is stationary. We will be looking at what is referred to as the identification problem, because we will see that all state space models are not identifiable in the sense that they are similar to another state space model. We will be also looking at methods of checking for diagnostics, that is, whether the model that we fit in is good enough or not. And finally, what we will be looking at would be prediction problems related to the state space models. So, how do you predict the future based on a given state space model? That is what we will be looking at in today's lecture. So, first we have the observation equation. So, x t is the observed time series, t running from 1 to n. So, we have n observations, and w t is a vector of state variables. So, there are d state variables w1 t, w2 d, w dt, and which we put into a vector form. Given this, we have the observation equation as x t is equal to alpha prime w t plus epsilon t, where epsilon t is white noise, that is with 0 mean and constant variance sigma epsilon square. Alpha, remember, is a vector of constants, that is x t is equal to summation over j alpha j into w j t plus epsilon t. We then have the state equation, where w t is equal to a matrix phi into w t minus 1 plus a matrix k into eta t. Remember that this w's are unobservable. So, the state equation as such is unobservable. It's a AR1 model, but it's based on unobservable variables. In this case, phi is a d by d matrix and k is a d by m matrix. So, together we have alpha, phi and k as the parameters of the model. In the second equation, that is the state equation, we have eta t, which acts as the error, and we have m such eta t's. So, we have eta t 1 to eta t m, which we put into the vector eta t, and we assume that these eta 1 to eta m, these are identically and independently distributed with 0 mean and sigma as the variance. Sigma is diagonal, with sigma 1 square to sigma m square as the diagonal elements. That really means that the etas are independent among themselves. We also assume that eta t is
independent of the epsilon t. That is, the errors in the observation equation and the state equation are independent of each other. Let us look at the condition of stationarity of this model. Now, if you look at xt, that is the first equation, and if we substitute the wt from the state equation in this, and remember that wt depends on wt minus 1, which again depends on wt minus 2, etc. So, if we keep on substituting this, what we ultimately land up with is xt is equal to alpha prime summation j is equal to 0 to infinity phi to the power of j k eta t minus j plus epsilon t. And if we use the backward shift operator b, then we can write eta t minus j as b to the power of j into eta t. So, we can make this representation of xt. Of course, we have the error term epsilon t as well. The process is stationary if phi to the power of j tends to 0 as j tends to infinity. This is similar to what we have seen in the case of the autoregressive or the ARMA processes. So, the result is the process xt can be said to be stationary if and only if all the eigenvalues of phi lie within the unit circle. So, let lambda be an eigenvalue. So, lambda must lie within the unit circle. So, in fact, in this case we will have several eigenvalues and all of them needs to lie within the unit circle. There will be d of them, remember, because phi is a d by d matrix. The process is said to be explosive if some of the lambdas lie outside the unit circle, and if some of the lambdas are on the unit circle, we say that the process is non-stationary but non-explosive. Of course, in the last case we assume that none of them are outside the unit circle. So, it may be that some of them are within the unit circle, some of them are on the unit circle, and some of them are outside the unit circle. So, we have a case of a non-stationary explosive process. But if they are just some of them are outside the unit circle, but not on them, we have a special case of explosive model, and some of them are on the unit circle, but not outside, then we have a non-stationary, non-explosive model. Only when all of them are within the unit circle do you say that the process is stationary, and this condition translates to the fact that phi to the power of j goes to 0 as j tends to infinity. So, that is the condition of stationarity of a state space model. Next, let us look at the mean and autocovariance function of the process. Of course, we will be looking at the mean and autocovariance function only if the process is stationary. So, assume that the process is stationary. In any condition, of course, expectation of xt is going to be 0, because if we look at the last representation where we represented xt in terms of the eta t's and the epsilon t's, eta t and epsilon t each have expectation 0, and hence it will translate to the fact that expectation of xt is equal to 0. And using the same equation, we can show that gamma h will be alpha prime phi h summation j equal to 0 to infinity phi to the power of j k sigma k prime phi prime to the power of j into alpha if h is greater than 0. That is, if we are taking a positive lag. But if the lag is 0, this boils down to looking at the variance, which is gamma naught, that is the variance of xt. In that case, of course, this function j becomes equal to j plus h, so h is 0 in this case. So the first term does not have phi to the power of h, but in this case we have epsilon t coming in from both xt and the other xt plus h, where h is 0. So there would be a contribution of epsilon t, which comes out to be sigma epsilon square. In the first case, of course, there would be epsilon t and epsilon t plus h are independent of each other, and therefore that contribution does not come in. So this becomes the variance and covariance of xt. Next, let us look at the problem of identification. Now let us try and understand why do we have such a problem in this model. Let F be any d by d non-singular matrix. And we define alpha star as F times alpha, Wt star as F inverse prime Wt, phi star as F inverse prime phi F prime, and K star as F inverse prime K. If we do that, suppose we write the observation equation in terms of alpha star and Wt star. So instead of alpha and W, we are writing the observation equation in terms of these two new variables. Mind you, Wt is not observed, and so Wt star is also not observed. So anything on the right hand side here in the first equation is not observed. So we can as well write it in terms of alpha and W as we can in terms of alpha star and W star. So suppose we write it this way and call this equation 1. But see that alpha star is alpha f into alpha, and therefore it's alpha prime F inverse prime Wt plus epsilon t. So this translates to xt being equal to alpha prime Wt plus epsilon t. Similarly, when you look at the state equation, which we now look at from the Wt star point of view, Wt star is phi star Wt minus 1 star plus K star eta t. Remember that nothing in this equation is observed. So if you write it in terms of this Wt star, it's fine, but if we substitute the values again, we find that we can write the same equation equivalently as Wt equal to phi Wt minus 1 plus K eta t. We will call this 4. Now what is the problem here? Look at equations 1 and 2 and look at equations 3 and 4. 1 and 2 are the state and observation and state equation in terms of Wt stars and the other parameters, whereas 3 and 4 are in terms of the original Wt's, and they are identical. So when we estimate the parameters, the question would be, what are we estimating? Are we estimating alpha star, phi star, K star from the given data set x t, or are we estimating alpha, phi and K? Because we cannot identify one from the other. Okay? The first one translates into the second set, and mind you, there can be an infinite number of such possibilities, because F is any non-singular matrix. So if you take any non-singular matrix, you go to a different set. So how do you actually identify a particular estimate with a given model. For that to happen, we need to impose restrictions which uniquely determine the model. One way that we can do it is we can write the model in the canonical form. The other way is that we can specify some of the parameters. Specifying some of the parameters really mean that we are putting restrictions on the parameters. So either through restrictions of the parameters or through some standard form, we can probably identify the model. Now, identification primarily, you know from your multivariate studies and from simultaneous equation model studies, requires some restrictions. And these restrictions, very often, if you look at what you do in factor analysis, for instance, you make a number of parameters in the dispersion matrix equal to 0. So you look at a model where you have a large number of parameters equal to 0, and then because that reduces the number of unknown parameters, and that way you can basically identify a model. So there are different techniques of doing this, which we will not go into in great details in this study. But these are the two methods by which we can actually identify a given model. But then identification is necessary before you actually estimate the parameters. Otherwise, as we just saw, we will not be sure as to what we exactly are estimating. Having done the estimation using the Kalman filters as we have discussed before, we need to have some diagnostic checking. So before we do that, we need to define what the residuals are. So in this case, we will write Et is equal to xt minus alpha prime Wt given t minus 1. Remember, Wt given t minus 1 is the conditional value of Wt given the past values t minus 1. So it's a sort of a predictor that we get from the Kalman filters. And substituting this for Wt in the first equation, this is the observation equation, we can get epsilon t is equal to xt minus alpha prime Wt given t minus 1, and that is what we call as the residuals, because we are now substituting Wt by its predicted value. Now, for a correctly specified model, this residual should be random with 0 mean and variance Vt, and it should preferably be normal. Now, what is Vt? Vt again we have calculated before from the Kalman filters. Vt is alpha prime Ct given t minus 1 into alpha plus sigma epsilon square. Again, remember that Ct given t minus 1 is the conditional covariance of, or covariance matrix in this case, of W. Okay. So we again use this to get the variance of epsilon t, which is Vt. Now, for sufficiently large n, the standardized estimated residuals is given by Et hat is xt minus alpha hat prime Wt given t minus 1 by square root of the variance of Et. Remember that in this case you can see that in the numerator we have Et, and in the denominator we have the standard error or the standard deviation of Et. But in this case, the parameters would be unknown, therefore, we are taking the estimated values of alpha and sigma epsilon square, and that gives us the estimated residual, which is standardized by the standard deviation of epsilon t. And it can be shown that this is approximately a normal 0-1 variable, and we need to check the usual normality check for this epsilon t hats to ensure that the residuals we get satisfy the conditions that we have imposed. But we can also do a formal test on this, and this would be to get a plot of the residuals to see if they are pattern free. Now, if the residuals are not pattern free, that means there is some mechanism which is underlying the residuals, and we will not be able to say that they are IID in that case. Now, very often a plot does not give us a very good idea, or we are not able to correctly read the plot always. For this, let REH be the hth order sample autocorrelation of the residuals. So, what we do is, now we are treating the residuals as a given series and then computing the autocorrelations from this residuals, and REH is the hth lag autocorrelation. And now we base the portmanteau test on this REH. So, the portmanteau test comes out to be Q is equal to N summation H is equal to 1 to M RE hat square H, and we know that this is chi square with m degrees of freedom, where m is sufficiently large, because we know that as H becomes very large, then this REH would become very small, and hence we can neglect the higher values. So, choosing m suitably large, we can do the portmanteau test and then reject randomness of errors if Q is greater than the tabulated value of chi square m alpha. Of course, we can do other types of tests like the Jung box test here. So, there are alternative tests for checking randomness. So, the primary idea is that we are checking the randomness of the E hat. So, you can use any of the alternative tests for doing that. Next, let us go over to model selection problems. For similar models, order selections can be done either through backward elimination. So, what you do is you fit a fairly high order model and then you start pruning this. That is, if you have the very high orders with insignificant coefficients, you drop these terms one by one, and then you make the model smaller. So, you can expect that the higher orders would be generally will have less effect than the lower orders. It is the recent past, and then you can choose the model accordingly. The alternative is to use the AIC and to use a model which minimizes the AIC. Remember, the AIC is minus twice the maximized log likelihood value plus the number of parameters. So, if you increase the number of parameters, so if you have a very large model, the maximized log likelihood may be small. In this case, of course, the maximum log likelihood itself will be large, but minus twice the maximum log likelihood would be small, but the number of parameters would be large, and hence there would be a trade-off, and minimizing the AIC would really lead to a model where we do not have unnecessarily too many parameters or variables involved. The AIC can also be used to select among disparate models. What's meant by this? What we have been assuming is that we have a same type of model say a ARP model, and we want to choose P. That is what we did previously. But we can have alternative models, like we can have a ARP model, we can have a ARMA PQ model, we can have a basic structural model. So there can be alternative models under the state space setup, and the AIC can be used to choose among them. The one with the smallest AIC value can be chosen. However, you should be careful that the likelihood in each of these cases is based on the same number of observations. This is because if you have different orders, for instance, if you are having a model which is ARP, then you have to discard P of the observations before you can fit in the model. So the first P observations goes, and you are given N observations, you just are left with N minus P observations to estimate the parameters. Alternatively, if you are using a MAQ, you will be using N minus Q of the observations to estimate its parameters. So there will be different sample sizes, effective sample sizes, and you cannot compare these models when you have different effective sample sizes. So you should be careful on this point. Finally, let us come to predictions. So suppose we have got a nicely fitted model, and we are given observations x1, x2, xn. Now how do you predict the future values of xn? Okay. Let's start with the next value, that is xn plus 1. How do you predict that? From the prediction equations of the Kalman filters, we can predict the latent vector w as wn plus 1 given wn is phi of wn. So given the n observations, we know wn, this vector, phi times that would be the predicted value of wn plus 1, which you denote as wn plus 1 given n. And this is what we have done in the Kalman filters. We have shown this. Therefore, xn plus 1 given n would be, if we use wn plus 1 given n instead of wn in the model, in the observational equation, we get the predicted value of xn plus 1, which turns out to be alpha prime phi wn. Now, since wn plus s is equal to phi s, wn, etc., we can go on just substituting this one at a time to get this equation. We can predict wn plus s. If you look at the expected value of this, this is basically phi s wn, and hence the predicted value of wn plus s can be based on wn itself. So we get the predictor of this by estimating wn by small wn, which we can get from the Kalman filters. We have wn plus s given n is phi to the power of s into wn. See that it is similar to what we do in s steps ahead prediction in the ARMA model or the AR model. If you look at the ARP model, and if you are trying to do or let us look at a simple AR1 model with a parameter alpha, and if you want to predict s steps ahead, then the predicted xn plus s value would be equal to alpha to the power of s into xn. We get a similar sort of result for the prediction of w in this case, because w again is, if you look at the state space model, it's a one step AR1 model. And hence from here we can, for any general xn plus s, we can predict that given xn as alpha prime phi to the power of s wn. This is referred to as the optimal predictor for xn plus s. Problem here is that the parameters alpha and phi would be unknown. So, what we do is we replace the parameters alpha and phi by their estimates alpha hat and phi hat, and we get x n plus s given n as the estimated predictor. What would be the estimated prediction error? That would be the MSE of x, or its expectation of x n plus s minus the predicted value, that is x n plus s given n, a square of that, and that simplifies to expectation of these three terms here, square of those. But look at these three terms here. You see that the first term depends on the past values, the second term depends on the future values of eta, and the third term depends on epsilon n plus s, and hence these three terms are independent of each other. So, when you take the square of them and take the correlation, expectation in this case, being uncorrelated, this cross product terms would be 0, and the MSE turns out to be simply an expression of this type. So, that would be the prediction error for estimating x n plus s. Let us look at an example, the AR2 model. So, here x t is alpha 1 x t minus 1 plus alpha 2 x t minus 2 plus epsilon t, and to put it into the state space form, we have w t, we have the alpha and k defined as a 0 1 vector, we have phi as defined as 0 1 alpha 2 alpha 1, and since x n is alpha prime w n, which is w n basically, and if we put that back into the prediction formulas, we see that for one step prediction, x n plus 1 given n would be alpha 1 x n plus alpha 2 x n minus 1. What about the two step predictor? X n plus 2 given n would be x 2 plus alpha 1 square x n plus alpha 1 alpha 2 x n minus 1. Remember that we cannot go beyond x n because that is not observed, but we can write it in terms of x n plus 1, which should be similar to what we did before. In this case, of course, x n plus 1 has to be the predicted value of x n plus 1. So, if we can write x n plus 2 given n as alpha 1, the predicted value of x n plus 1 plus alpha 2 into x n. So, that is how we can actually do the prediction for the AR2 and for a general state space model.
In today's lecture, we have discussed the stationarity property of the state space model. We have seen how we can identify a state space model, or what are the problems related to this identification. We have also seen how we can select a proper model, as well as to check for the residuals and the properties of this model, how good the model fit is. So, we have done some diagnostic checking as well. And finally, we have looked at the predictions based on a state space model. Now, over the last 3 lectures, we had been discussing the state space model, and we have seen that it encompasses a wide set of models, including the Box-Jenkins model. So, a state space model is a more generic type of model, where other time series model comes out as special cases.